Okay, I'll have your exams back on Wednesday. They're graded. I just have to do some assessment stuff and get the answer key online. Also this week I'm going to be working towards getting all the participation points from the first 3 chapters into Canvas, so that's going to take a little bit of time. But I want to finish up chapter 4 today, and then I'll send out an email for the reading for chapter 5. I released it along with the homework problems yesterday. For chapter 4, let's make the chapter 4 homework problems due by Friday to finish the chapter up. I can't, as much as I would like to put a deadline on each one of these chapters, when I do, as soon as the deadline hits, it disappears. And then I bring it back, and then it disappears, and I bring it back. So I don't even want to mess with it. I'll just tell you when it's due, and if you want to take the calculated risk that I won't get to doing the participation stuff on that day, you can go ahead and gamble. But
chapter 4 still set back in unlimited attempts.
Unlimited attempts? Oh, you should take that bargain.
It says no back.
No, you should still take that bargain. I'll fix it. I'll fix it after class. I change these things, and then I don't know how they end up changing around. Okay, so we were talking about chapter 4 last Monday. And the idea here is that if I had an acid-base equilibrium where this is my equilibrium equation, how do I push this equilibrium to the right and make a stronger acid? Now, before you answer, today, and from as long as I remember to bring this, we're going to have a little more fun, because behind the curtain is the giant roulette wheel that has everybody's name on it. So that means if I was going to ask that question, I could push the button.
Olivia Talamo.
That will speak the name. So what do you think? So I want to push the equilibrium to the right to make a stronger acid. So what do I need to do?
Make a weaker base.
Make A minus a weaker base? I'll accept that. So I'd want to make A minus a weaker base, but how do I do that? I'm going to wear this out. Oh, said Carolyn. So how am I going to make A minus a weaker base? Make it.
Does this have to do with the concentration?
No, that's one thing I can't do here. Is I can't use Le Chatelier's principle. I have to do something to A minus to push the equilibrium to the right. Okay, get some help for you.
Amanda Kocher.
All right. One of you guys had your hands up.
Stabilize.
Make A minus more stable. So the more stable we can make A minus, two things will happen. It will become a weaker base, and then HA would become a stronger acid. So the more stable we make A minus, the more we push the equilibrium to the right. the more H plus we make, and the stronger HA is as an acid. Okay. So what we're going to do is we're going to go through all the different ways that I can make A minus more stable. Okay. And we talked a little bit about that last time in terms of taking, for instance, an acetic acid and maybe substituting that with 3 fluorines to make trifluoroacetic acid. An acetic acid is okay as an acid, but trifluoroacetic acid is wicked enough to burn your skin. So it's much stronger. So if I write that equilibrium for each, well, I'll just write it in one combined one here, that I've got, every time I attach a halogen, or replace a halogen with one of those hydrogens attached to the acetic acid, I'm going to make a stronger acid. And the more halogens I put there, the more electronegative the halogens, the stronger the acid's going to be. And therefore, the more stable the base is going to be, the more stable the conjugate base. So why was that?
It distributes the negative charge, so like it's not all in one spot. It's just kind of
Okay, so we're going to take, first of all, I'm delocalizing that charge anyway, because there's the resonance hybrid of the two structures. So when I add a halogen like a fluorine to that, it's distributing the charge even more. Because what's happening? The fluorine's removing electron density from the carbon, and then that carbon can remove electron density from the carboxylate, from the deprotonated carboxylic acid. Okay. So anything I can do to pull negative charge away from the negative charge of the base will stabilize it. Does that make sense? So what I'm doing is I'm delocalizing the charge. This is one way of doing that. And this way is through basically through electronegativity. And if I do that, if I redistribute the charge through electronegativity, that is what is called an inductive way of doing things, or an inductive effect. So what I'm doing is I'm spreading out the negative charge to the fluorines using the electronegativity of the fluorine in doing that. There's another way to do this if I could draw resonance structures that did the same thing. And that's what's called resonance. Okay. So the more electronegative the element, the more electronegative elements I have, the stronger the acetic acid is going to become. And that's kind of where we left it off on last Monday. But what I want to emphasize here is that the way to make the base, while the way to push the equilibrium is to make the conjugate base more stable, the way to do that is by distributing the negative charge of the base and delocalizing it throughout the molecule. So I'm going to pull electron density out. And anytime I can do that, I'm going to make a stronger acid because I'm making a more stable base. Okay. So are we all kind of on the same page here? Yes? Okay, so let me give you some oxygen bases where the negative charge is on the oxygen. So how about I start with, well, let's do alkoxides. Let's do an alkoxide. And let's compare. Now, an alkoxide is a deprotonated alcohol. So just from the stability standpoint, let me draw two alkoxides to come from two different alcohols. The one on the left is what kind of alkoxide? Primary, secondary, tertiary. Primary. And the one on the right is tertiary. So my question is, which one of these is more stable? Okay. Which one of those two bases is more stable? The primary one or the tertiary one? I'll give you 2 minutes to think about it and to answer. So I want to know which one of those two is more stable. And while you're thinking about that, you may want to think about the next question that I'm going to ask, which is, why do you think that? I think that's everybody. So let's see what we've got. We have most of everybody said B. That B is more stable. And 4 people who said A was more stable. So how am I going to answer that question? I'm going to do the same analysis that I did with with the halogen. So tell me about the carbon-hydrogen bond in an alkyl group. For the alkyl group, which atoms are delta plus and which one's delta minus? What's delta plus?
Delta plus.
So the hydrogens are all delta plus, and that makes the carbon delta minus. Okay, so on this alkyl group then what I have is I have a delta minus carbon. Is that helpful in stabilizing the O minus charge of the alkoxide? Is having that carbon with a slightly negative charge helpful? I see a yes and I see a no. I see no's.
Wouldn't it be more helpful because it's going to spread out the negative charge, which makes the base more stable?
Yes, if it's going to get some negative charge. So right now, the negative charge we gave it didn't come from the oxygen. It came from the 3 hydrogens it's attached to. So now what I'd like to do is I'd like to take some of that negative charge from the oxygen and I'd like to spread it out into that carbon. And how happy is that carbon going to be to get that negative charge? It would like to do what with its negative charge? This carbon with its negative charge, what would it like to do? It'd like to push it onto something else, right? I don't know why I say right. It's not necessarily obvious that it's right. But it wants to push the electron density off. Where have we seen that? Yes. The stability of a carbocation. So if you have a carbocation, the more alkyl groups that you attach to that carbocation, the more stable it becomes, because now that carbon's got a place to push its electron density to. And everybody gets happy because the goal here is for all the atoms to be 0. Right? That's the goal. So when I put an alkyl group on an alkoxide, am I helping the situation? Am I stabilizing it? I'm doing exactly the opposite. Because the way I'd like the electrons to flow is like this, and instead what are they doing? I'm trying to push negative charge into a negatively charged thing, which doesn't work well. Does that make sense? What I'd really like is I'd really like something out here to be maybe positive, or for the negative charge to be pulled out of the O minus, because that will stabilize. Trying to push the O minus in, trying to push the negative charge in, isn't going to work. So what does that mean in terms of the stability of these two things? Every time you put an alkyl group on an alkoxide, the situation gets worse. So that, which one of these is the most stable? A turns out to be the most stable, and because B has more alkyl groups, it becomes less stable. Bobby?
You people said about every time you put more groups on something, it gets less stable.
It gets unstable. So one alkyl group with a negative charge kind of pushing in the opposite direction, really what we can think of is this negative charge is kind of trying to push into that oxygen. Or you can think of the O minus trying to push into the C minus. But either way, since they have the same charge, that doesn't work well. So the more of those alkyl groups you put on this carbon of the alkoxide, the less stable it's going to be. So the best case scenario for an alkoxide would be, best case scenario for an alkoxide would be, don't have a carbon attached to it. But if you need to have a carbon attached to it, just make it a CH3 of like methanol, so that methanol would be the strongest acid because it makes the most stable conjugate base alkoxide. But hydroxide would be an even stronger base. So this is an inductive effect as well, because those atoms have delta minus charges and they're pushing. But they're pushing in the wrong direction. So when we look at alkoxides, or when we look at alcohols, the most stable, or the strongest acid of the alcohols would be primary, and the weakest would be tertiary. everybody with me? So again, how do you stabilize something with a negative charge? Pull it away. Redistribute that negative charge by pulling it out. Okay. So, now let me give you more oxygen bases. So let's start with CH3OH. Nope. We'll do this as stability. So methoxide. Then let's go with a deprotonated carboxylic acid, a carboxylate. Let's see. Then let's do this. Let's attach the O to a benzene ring. This is called a phenoxide. This one's called a carboxylate. And then our alkoxide. And then, let's see, I'm supposed to have 5 of these. Then let's go with this. Then that's called a sulfonate. So if I put hydrogens on these, they make 4 different oxygen acids. The sulfonate would become a sulfonic acid. The phenoxide would become a phenol. The carboxylate would become a carboxylic acid, and the alkoxide would become an alcohol. So my question is, of A, B, C, and D, which one do you think is the most stable anion? Which is the most stable structure? A, B, C, or D? What I'd really like you to do is to rank them from strongest down to weakest. So, let's see, we've got 4 of those. So let's go ahead and I'll send that out. Although I need to shrink it. There. So that's my question. My question is, bless you. My question is, we're going to rank these, but I'd like you to rank them, and then we're going to go through them. Then we'll go through them one at a time. And I'll ask you which one's the most stable. Okay, so I'll give you 2 minutes to think about this. Most stable to least stable. And what criteria are you using to base that ranking on?
But we're only putting in the most stable one?
Right. You're going to put in the most stable one right now. But what I'd like you to think about is the ranking, because once I look at the most stable one, then the next one I'm going to have you do is the next most stable, and the next most stable, and then the least stable, if we get that far. And again, remember the key. What kind of factors will stabilize this? Okay, if you can go ahead and tell me which one is the most stable, then we'll work from there. Okay, the most stable one is, a tie. A tie between A and B. A being the alkoxide or A and D being the sulfonate. Okay, that's fine. Let's investigate that a little bit more. So, does anybody want to volunteer and answer why they chose A? A. Anybody want to choose an answer or give me an answer for if they chose D? Sarah?
Because you said to like stabilize, you have to like spread out the negative charge, and like with the oxygen and the sulfur, you could do that.
Okay. So you want to say how you would do that?
So like the electronegativity is like they're each like fully, because they all want like the negative charge, so it like distributes out the carbon, so they push it away.
Okay. There's a very specific way we can do that though. So I want to put a full-blown negative charge on each one of those oxygens. Now I can't, right, because I only have one negative charge. But if I wanted to put a maximum of, let's say, minus a third, how would I do that? So let's draw resonance structures. So let's spread it out that way. So you could very easily say, oh, well, I'm going to move this pair of electrons here, move that pair of electrons there. And then my double bond will be there, and my double bond will be there. And then, oh, well, let's move this pair of electrons here and move that pair of electrons out there. Right? And so that would put a double bond there, and then the O minus there. So I can write an additional 2 resonance structures that puts the negative charge on each one of the 3 oxygens. Now, is that the real structure of the molecule? No, the real structure is the resonance hybrid. So if I wanted to draw the resonance hybrid of that, what would I do? Well, I would write all single bonds first, and then I'd take the average of the charges. So what's the average of the charges going to look like? Each oxygen is going to be a, okay, I don't care about the exact number. Exactly, a delta minus. Partial negative on each of the oxygens. Now what about as far as bonds go? What's the average bond between a sulfur and an oxygen? Well, I'm talking about single, double, triple. I'm talking about the bond, single, double, or triple bond. I need a partial bond on all three? Yeah. So between a single and a double bond on all three of those. So this is a way, by drawing these resonance structures, what have I done? I've spread out the negative charge. And I've made the molecule more stable. So not only can you do this with electronegativity effects, you can also do this by resonance, which is kind of the key to answering this question. How can I do this with resonance? And there's the first example. Do people want to withdraw their A answers? No, because nobody's going to admit they chose A. Okay, let's do... So, is D the most stable? I will say with authority, yes, it's the most stable. So now your choices are, let's see, your choices are going to be, after I choose the correct answer, oh, people are already taking away from A. And moving more towards D. Go ahead. Go ahead. Make them all D. Well, okay, there you go. There you go, perfect. Now I'm going to close that question. And when I mark it as correct, I'm going to go back and give everybody participation points. But it just helps me. Okay, next question then. Of A, B, and C, which one is the next most stable one? A, B, or C? I'll give you a minute. So what we just learned from D, apply that to the remaining three. Which one would be next most stable? Your time's just about running out. Okay, final vote. Going once, twice. So B is our most popular choice, along with C and an A. So it's between B and C. I'll do the same thing. Did somebody who chose B want to give me their answer?
It as well has the most number of resonance structures where you can distribute the negative charge to oxygens.
Does somebody want to take a disagreement with that statement?
The number of resonance structures doesn't matter. That's what it's going.
Well, not so much from that, but does it have the most number of resonance structures? Wait, you qualified that. It has the greatest number of resonance structures where
the negative charge can be spread out between the oxygens.
Where it can be spread out between the oxygens. Yeah.
If you have a whole bunch of resonance structures on C with the benzene.
Okay, exactly. So, I should probably listen to the answer before I criticize. Probably a good rule for life, but... So, there's the resonance hybrid for that one, for that carboxylate. Now, how many additional resonance structures could you draw for C? How many?
David Sprenger.
3? Do we agree? Okay. So how would I do that? I would take this pair of electrons, go here, move that pair of electrons there. That should look familiar from recent past, right? Kind of the reason why we're kind of mixing in these fundamental things early. So there's 3 more of those I could draw, but what's the problem with those resonance structures? They don't have...
They're attached to carbon capital, so it'll bring it down because the charge won't be distributed the way you want it to.
Well, it's distributed, but it's distributed over what kind of element? Carbon. And so we go back to those fundamental rules about what makes resonance structures more or less stable. We get to rule 3, which says what? The negative charge probably wants to go with the more electronegative atom. So that, in this case, spreading the charge over the carbon is not nearly as helpful or stabilizing as spreading the negative charge over the oxygens. And that approach will work for us now. There's also later on going to be in next semester when we talk about benzene rings. Benzene rings are super stable because they've got the double bond, single bond, double bond alternating, and that's what's called conjugation. And so a benzene ring is really, really stable because of that conjugation. And by putting that negative charge in the ring, I bust that up. But we'll just stick with, I'm putting a negative charge on a carbon over an oxygen for the moment. So that's going to make B then, this was number 1, right? Stable. B will be number 2. And then what about comparing C and A? Number 3 would be the phenoxide. Oh, you don't like that? Okay, let's vote. Let me close the question and we can vote on that. So now between A and C, vote for the third most stable. Okay. So this is the one that is not the least stable. This is the third most stable one. So what's more stable, phenoxide or alkoxide? Okay. 19 people say 3 and 9 people say A. Why C?
It has a resonance structure that it can't spread out to.
Because it's got 3 resonance structures. And 3 resonance structures beats 0 resonance structures. So between B and C, the number of resonance structures exactly didn't matter. It was the kind of resonance structure it was. But now between C and A, the fact that it does have resonance structures makes it more stable than those that don't. And we'll actually find that out. We're going to do, what are we doing? In lab, we're going to separate the components of an Excedrin tablet here in the next week or so for a couple weeks. And what we're going to find is that we can actually deprotonate a phenol with OH minus, but we can't deprotonate an alcohol with OH minus. So that shows you how much stronger the phenol is as an acid relative to the alcohol. We just can't deprotonate alcohols unless we use some really strong bases that we'll get to probably at the end of the semester.
So the idea of, when we're looking at relative stabilities, the idea of extra alkyl groups attached to the carbon with the substitution with a negative is below in ranking of resonance structure?
Much lower.
Okay.
Much lower. So this is number 4, and this is number 3.
Before when you were talking about the primary, tertiary carbons, so that only comes into play if they don't have resonance structures?
Right. That's what I would do. If I gave you a primary, secondary, and tertiary alkoxides, then you would use the pushing of electron density by the alkyl groups. We went from a small, narrow look to now a big, broad look of all oxygen acids and bases. And so the theme here is resonance.
Okay.
That's a decider. And my point throughout this entire, about the going through this and taking the time to go through this, is that we have to think about what we can do to make A minus, to make that conjugate base more stable. And what tricks do we have? Well, the overarching thing is to make O minus more stable is to suck the electron density out of it. How do you do that? Well, you could do that through electronegativity effects. And the idea of the alkyl groups is the alkyl group isn't sucking any electron density out. It's going in the opposite direction, so the more I put on there, the worse the situation. But if I put electronegative groups, or if I use resonance, I can now pull the electron density out, make the conjugate base more stable, make its corresponding acid stronger. So it's kind of like a toolkit. How do I make it more stable and make the acid stronger? Use resonance, use induction, but pull the electron density out. Don't push it back in. That's the big takeaway here. Everybody okay? So now let's go to what I'm working through is the remaining problems here. So we did alcohols, we did oxygen species. Now, how about phenols? So here is a phenol. Here are 3 phenols. Phenol is an OH attached to a benzene ring. Now, the question here is, which one of these, you're supposed to match the pKa with the acid. Okay. The acid with the lowest pKa is going to be what acid? Strongest or weakest? Low pKa means stronger. Stronger acid means what kind of conjugate base? Weaker or more stable. Okay. There's no shame in having to sit down and map those inverse relationships out so you can keep track of them in your head. Lower pKa, stronger acid, weaker base, more stable base. So really in this question I could say, let's put negative charges on all three of these. Which is the most stable? So if I turn these into phenoxides by putting an O- on there, which one's the most stable? Give me a guess. B. Why?
Because it has a positively charged nitrogen attached to the ring, so we can distribute the negative charge around into the acid.
So I've got to go through the ring to distribute the negative charge. If I have a nitro group, and that's what this is an NO2, the nitrogen itself is positively charged, so that's inductively pulling electron density through an electronegativity. But you could also think that maybe for this nitrogen-oxygen double bond, if you move a pair of electrons to the oxygen, you might be able to draw a resonance structure. So a nitro group we're going to find is a very powerful electron-sucking group, electron-withdrawing group, because it has elements of induction and resonance. So it would be the most stable phenoxide, which means its acid would be the strongest acid. What about the C with the CH3 group? What's going to happen with the CH3 group?
Wouldn't it be the weakest?
Be the weakest because what's the CH3 group doing?
It has a partial negative charge on the carbon, pushing and repelling the other negative charge.
Well, it's pushing back into the ring negative charge, and I want to pull the negative charge out of the ring. So in this case, the strongest acid would be B, the next strongest acid would be A, and the weakest would be C. Because of the effects of those groups. So again, this is just another application of those principles. You want to make the conjugate base more stable, suck the electron density out of it. You want to make it less stable, try and push some in. And then I'll leave you with the last question, which is about amines and the pKb's, and why are they so small? They are really small. Now, pKb is exactly the opposite situation. When you have a pKb equilibrium, you have a base picking up a proton to form the ammonium, to form the positively charged species. So if I have the positively charged species, what do I want to do?
There's no difference between A or C.
Yeah, there should be. There should be. I don't know why there isn't. Good thing we're not answering this. But because you're going to finish up your chapter 4 problems, so when you're looking at amines with pKb's, I've now reversed it and I now have a positive species, and I'm trying to stabilize that by now pushing electron density into the positive charge. So everything reverses. In the pKb equilibrium, yes. Okay?
More methyl groups.
So more methyl groups would make it more stable. Except there's a cutoff of that. All right, I will send out the chapter 5 reading for Friday or for Wednesday. We are now back to my traditional class. So I will start putting my videos into the textbook, because for confirmations that you'll see there's a whole video that now goes with that. So if you've been like, there'll be extra because from here on out, it's traditional. Right? So then we'll talk about that on Wednesday.
So is just the homework on